Hello and welcome to another WJEC A level physics question. This is question 5 from January 2012's Unit 4, and it's about electrical fields and potentials, which is also currently in Unit 4. So the original diagram had a plus 57 microcoulomb charge, isolated positive charge there, and we were asked to draw some electric field lines and equipotential surfaces for the positive charge. So I pre-drawn these just to save a little bit of time. The equipotential surfaces are concentric circles around the centre of the charge, and I've labelled those here. And the field lines are the lines pointing radially outwards. Now the reason why the lines are radially outwards is that the direction of a field line is the direction in which a positive charge would move. So if I put a positive charge anywhere near this positive 57 microcoulomb charge, it's going to be repelled and therefore would be pushed away. So the field lines have to be outwards. Generally on this type of question, WJEC likes at least 3 surfaces and 3 field lines, so that's why I've drawn 3 of each there. You could draw more if you like. Next, we've got to state one difference between this diagram and the equivalent diagram for the gravitational field strength due to a spherical mass. Well, gravitational fields are always attractive, so with gravitational fields, the field lines would be inwards. The equipotential surfaces don't have a direction, so they would still basically be the same for a gravitational field. For part C, we've got to calculate the magnitude of the electric field strength at 15.8 centimeters from the centre of the charge. The formula for electric field strength is E equals 1 over 4 pi epsilon naught Q over R squared. 1 over epsilon naught is taken as 9 times 10 to the 9. The charge is 57 microcoulombs, micro 10 to the minus 6. And the distance here was 15.8 centimeters. So we've got to remember to turn that into meters. So let's put those values into the calculator and see what we come up with. So we end up there with about 20.5 million. So 20.5, and we can either have volts per meter or newtons per coulomb for the unit. To calculate the electrical potential at the same distance, we use the formula that VE is 1 over 4 pi epsilon naught Q over R. So it's going to be 9 times 10 to the 9 times the 57 times 10 to the minus 6, but just divided by 15.8 times 10 to the minus 2. So a quick way of getting this answer is just simply to multiply your previous answer by 15.8 times 10 to the minus 2. The only difference between the two calculations is the squared on the bottom there. So if we put that in, we end up with 3.2 mega, and this will be volts or possibly joules per coulomb, but the standard unit is the volt. Next we're asked to state the potential a large infinite distance away from the 57 microcoulomb charge. Well, if we understand the definition of electrical potential at a point, which is the work done in moving a unit positive charge from infinity to that point, then automatically the potential at infinity is 0. If you're already at infinity, you don't need to do any work in moving a charge to infinity. For the last part of the question, a 2.45 microcoulomb charge is placed at that 15.8 centimeter distance away from the 57 microcoulomb charge and released. We're going to use our answers to D to calculate the final kinetic energy of the point charge when it's travelled a large distance away from the 57 microcoulomb charge. Well, in terms of energy here, what we've got is that electrical potential energy at the 15.8 centimeters will turn into kinetic energy as the charge moves away from the 57 microcoulomb charge. At infinity, because it has 0 potential energy, all of that energy will be kinetic. So let's just put down a brief summary of that. I will say that all of the potential energy will turn into kinetic energy when the charge reaches infinity. So the kinetic energy at infinity is going to be The change of potential, 3.2 times 10 to the 6 volts, going from plus 3.2 times 10 to the minus 6 volts down to 0, multiplied by the charge that we're moving, the 2.45 microcoulombs. So you can see that those values will cancel. And if we multiply the values together, we get 7.95 joules. Effectively, what we're doing here is using the equation W equals Q times delta V. The work done in moving the charge from the 15.8 centimeters to infinity. In other words, the gain of kinetic energy of that charge is simply found by multiplying the charge that we move by the potential difference between the two places. So once again, thank you very much for listening. Please remember to like and subscribe, and feel free to add any questions. Goodbye.